Okay, I'm not teaching you right now because I'm doing something else, but I'm going to teach you on the big screen. So get your books out, make sure you've written down the title. We're practicing Le Chatelier's principle. By the end of the lesson, hopefully we'll be able to practice applying Le Chatelier's principle to a variety of situations. But to start off, can you answer these summary questions from the last couple of lessons? All I want you to do is answer these questions. So, question number 1. The reaction between sulfur dioxide and oxygen to form sulfur trioxide can be modelled by this equation. 2SO2 plus O2, reversible reaction sign 2SO3. Explain why this reaction models a reversible reaction. Explain the meaning of the term reversible in the context of chemical reactions. And the reaction between iron, 2 ions, and silver ions is reversible. Here we have Fe2 plus Ag plus, then that goes to Fe3 plus Ag. Iron 2 nitrate solution is pale green, and iron 3 nitrate is orange brown. Describe what you observe when iron 2 nitrate is mixed with silver nitrate solution. Teacher, please pause this and let them answer the questions. Okay, so answer the questions. Okay, you done? Excellent. Let me add the little pen thing so I can annotate. Okay, so how do we know this equation models a reversible reaction? You know it models a reversible reaction because we have this thing here. This is the reversible reaction sign. Explain the meaning of the term reversible in the context of chemical reaction. A reversible reaction is when reactions can form products, but products can turn back into reactants. Excellent. The reaction between iron 2 ions and silver ions is reversible. We have Fe2 plus Aq plus Ag, Aq, reversible reaction thing, Fe3 plus Aq plus Ags. Different. Iron 2 nitrate, this is iron 2, you can tell because it's got the 2, is pale green. And iron 3 nitrate is orange brown, this is iron 3. Describe what you observe when iron 2 nitrate is mixed with silver nitrate ions. Okay, so here we have iron 2, we add silver nitrate, well, it turns to iron 3. So what you would observe was that the solution turns orange-brown. But there's something else. It's a chemical reaction. What are the signs of a chemical reaction? Anyone? Joe? No. Okay, the signs of a chemical reaction are, one of them is a precipitate formed. And here is our precipitate. The precipitate, we know it's precipitate because the S is solid. So we have a solid that is formed. Excellent. Okay, so before we do any more, we'll discard the annotations. You hopefully should be given a piece of paper by your teacher, and it looks like this: methanol pitch. And we're going to work through the methanol pitch questions together. I'm going to give you some hints and tips on how to do this. In this activity, you will find out the optimum reaction conditions for producing a high yield of a product in a reversible reaction, and why compromise conditions are often used in industrial processes. Basically, that means if your job is to make some chemicals, if your job is you're a chemical engineer and you have to make chemicals, you want to do it in the best possible way. If you're cooking an egg, you can cook an egg by turning the gas right down to the smallest flame, and if you put the egg in the pan, it will cook, but it will cook really slowly. It may take 10 or 20 minutes for you to be able to cook your egg. But if you turn it right up really high, you'll be able to frazzle the egg, and it's raw on one side and cooked on the other. So getting the right conditions is like cooking. If you do it too low, it's too slow. If you do it too high, it's too fast. But with cooking, you can turn up the temperature and you can chop things up. With reactions, we can increase the pressure, we can increase the temperature, we can increase the concentration, and changing them will have different effects on how fast things cook. So so let's go and look at these questions. So setting the scene. Methanol is an important feedstock for making other chemicals and is used as fuel in racing vehicles such as monster trucks. Your teacher may want to pause the video to show you what a monster truck looks like in case you don't know. But basically, it's a really, really, really big truck with massive wheels. Wheels about as tall as you are. You don't have to do that. Here is the reaction. It is made by reacting carbon monoxide with hydrogen. Oops, I've just drawn on this. This is carbon monoxide, CO, and this is hydrogen. And it makes this methanol. So this, and it's a reversible reaction, okay? The equilibrium yield is the amount of desired product present in a reaction at equilibrium. It depends on the concentration of reactants, the pressure, and the temperature. Okay, so this is what we want to make, and these are the ingredients we use to make it. Okay, other thing to note, look at this. This delta H is the energy change. Remember, we have types of reaction. We have endothermic and exothermic. Which is this? The energy has gone down, so heat's been given out to the surroundings, so this is exo. Whereas this, the energy has gone up. It's had to take energy in from the surroundings, so this is endo. So this is negative, this one goes down, so this is an exothermic reaction. The forward reaction is exothermic. Right, let's scroll down. You're going to explain why methanol is manufactured at a pressure of 5 to 10 megapascals, which is 50 to 100 atmospheres, and at 250 degrees. The Chatelier's principle provides us with a rule to predict what happens to reactions at equilibrium when the conditions are changed. Complete the following sentence which explains the principle. When a change is made to a reaction at equilibrium, the position of equilibrium moves to something that changed. Pause, look back in the notes from previous lesson and work out what it is. Have you done that? It's difficult to write here because it's so not very good with this thing, but I think the word is counteract. Reverse, counteract, change. Let's use Le Chatelier's principle to predict whether a high or low pressure would produce a yield of methanol and explain your answers. You will need to use the balanced chemical equations to see how many moles of gas there are on each side of the equation. So this is our equation. See if I can fit it on here. So we've got CO2, no, it's not O2, CO plus 2H2 reversible reaction sign CH3OH. Okay, so first of all, let's work out how many molecules or moles we have each side. So this is H2, and there's two of them, so we have 2 molecules. This is just one CO, so we have 3 molecules this side, and this is a really big molecule, but we only have 1. So 3 molecules versus 1 molecule. So this is the side with fewer molecules. Now, check out Le Chatelier's principle for pressure. What happens when you lower the pressure? What happens when you increase the pressure? Basically, this question is saying, use Le Chatelier's principle to predict whether high or low pressure would produce a higher yield. You want the equilibrium to move to the right. You want the equilibrium to move to the side of CH3OH. That's what you need to find out. That's the side with the fewer molecules. Okay? So, what part of Le Chatelier's principle moves equilibrium to the side of the fewer molecules? Is it raising the pressure or is it decreasing the pressure? I can't remember this off the top of my head. So, pressure 1. Okay, if pressure Right, pause. Have a go. Have a go. Go on, have a go. Done it? Excellent. Right, now, here we go. If the pressure is increased, equilibrium shifts in the direction of the fewest molecules. So we need to, if we increase the pressure, increase pressure, it moves in the direction of the fewest molecules, which is this side, and therefore increases the amounts of methanol. So in this situation, to get the best out of this reaction, we want a high pressure. Now, B. Let's use Le Chatelier's principle to predict whether a high or low temperature would produce a high yield of methanol, and explain your answer. Okay, remember, the forward direction making methanol is exothermic. Forward, moving to the right, is exothermic. So what can you do to the reaction in terms of temperature that's going to move the position of equilibrium even more to the right, even more in the direction of the exothermic reactions? You want to make sure equilibrium moves to the right hand side, because that is where this is. So what can you do that will improve the reaction by moving it more into the exothermic reaction? Please, again, I need you to pause the video and try and answer this question. Done? I thought so. So, if you look at your Le Chatelier's principle, I'm checking it because I don't remember off the top of my head. If temperature is decreased, equilibrium shifts in the exothermic direction. So what you need to do is you need to decrease the temperature. Decrease temperature. You need to decrease the temperature. By decreasing the temperature, Le Chatelier's moves in the direction of the exothermic reaction, which is towards the CH3O3. So first of all, you want to increase the pressure. Now we want to decrease the temperature. Doing so will make us more meth. Explain why removing methanol from the equilibrium mixture causes the yield of methanol to increase. What does Le Chatelier's principle tell us? If you make a change to a system in dynamic equilibrium, the system will try and undo that change. So if you remove a product from the system, what happens? Sorry, some loud videos going on in the background. Explain why removing methanol causes the yield of methanol to increase. Pause. Do it. If it keeps beeping, it's running out of memory. Got to get it done soon. We done? What do you think the answer is, Jonah? No? Okay. Joe, are you asleep? Okay. Let's keep moving. Removing a product, or concentration, removing a product, concentration, shifts equilibrium, shifts equilibrium to undo that change. So basically, if you remove a product, the system goes, oh, I'm missing the product. Quick, let's make more, which is brilliant. If your job is to make methanol, or meth, by removing a product, your system tries to balance itself by making more product to put everything back to normal. So actually, it's a good, productive way of making things. We are nearly done with this little bit of me talking, so soon you'll have to do some by yourself. The actual let's try again. The actual conditions used are 50 to 100 atmospheres, with pressure at 250. Explain why these conditions are described as compromise conditions. Okay, so if you remember, we need high P, increasing P, but decrease T. So basically, if you increase the temperature, you decrease the pressure. If you decrease the pressure, hang on, if you increase the temperature, you increase the pressure. Sorry, mistake. If you increase the temperature, you increase the pressure. If you decrease the temperature, you decrease the pressure. But we want them to go in opposite ways. So there's no perfect. We can't have low temperature and high pressure because those things are kind of working against each other. So what we have to do is we have to kind of bring them along the middle. Meet them somewhere in the middle. And by meeting somewhere in the middle, you get a bit of a higher pressure and a bit of a lower temperature. And it's not perfect, but it's not bad. So conditions, they're difficult. It's very difficult. Ooh, that's not right. Yeah, difficult to get high pressure with low T. It's difficult to get high pressure with a low T, so therefore, boop, 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 compromise in between the two. The last question I'm going to walk you through, and then the rest you have to do yourself. I'll leave the answers with whoever's covering. Okay? So, a catalyst is a mixture of zinc oxide and copper oxide, and it's used in the process. State how the catalyst affects the rate of reaction and the yield of methanol. Remember, what does a catalyst do to the rate of reaction? And what does it do to the end product? Pause, discuss with the person next to you, have a go. Have you done that? Splendid. How does a catalyst change the rate of reaction? It increases the rate. Increases the rate. But how does it change the end product? No change. It just changes how fast it gets there. This thing is going to beep until I stop. Okay, so I've walked you through the demo questions. There are now more questions for you to practice yourself, and if you manage to finish all of those, there are even more questions on the PowerPoint. I will be back later. I'm sure you're doing really well. If you have any questions, just ask, sir or miss, whoever. Okay, love you, bye.